most of you who work in demography and demographic methods and statistical demography, there's no need to introduce Carl, but I'll just say a few words. I mean, Carl's sort of background is economics. He has a PhD in economics from Berkeley, and since then he held a lot of academic positions and visiting professorships in many institutions, but for a long time has been associated with the Florida State University, where he's now the director of the Center for Demography and Population Health. And also, you'll probably know Carl in his capacity of a long-standing editor of demography research. Today's topic of our webinar will link very closely with Carl's major area of interest, which is analyzing fertility, and especially fertility in the context of the Americas, fertility in the context of countries with not always ideal data availability and so on. So, and the topic for today is estimating total fertility from the shape of the age pyramid, Bayesian models and applications. So once again, live from Florida, my great pleasure to welcome Professor Carl Schmertmann. Carl, over to you.
Well, thank you very much. Good afternoon. I'm delighted to be here. I wish I could actually be in Southampton. That would be, preferable, but hopefully we'll meet each other in person soon. And in the meantime, happy to share with you virtually. Let me begin sharing. Are we okay? Am I sharing properly, Jakub? Hello?
Yes.
Everybody can see the title page?
Yes, thank you.
Oh, okay. Yeah, this is just like virtual class. No one answers when I ask a question. Okay, so I'm going to talk about estimating total fertility from age pyramids or from age-sex structures. This is a Bayesian approach. I want to recognize right off the bat that this is a kind of mashup of a couple of papers that were written with colleagues, including Matt Hauer, who is my colleague at FSU, Marta Azevedo, who is she's now retired, but was a demographer at the University of Campinas in Brazil, and Joe Potter at the University of Texas. The Marta and Joe in particular are the Brazil part of the talk that we'll get to in the second half. Okay, why would we bother trying to estimate total fertility from the age-sex distribution? The answer is missing data, basically. The standard formula needs births by mother's age. So you need some sort of a vital registration system or some kind of accounting for how old the mothers were of recent births. But a lot of places and circumstances, you don't have that. You often don't have these numerators that you need for several possible reasons. One is there isn't any vital registration system, or it's bad. You might have spotty data in sub-Saharan Africa or in Brazilian indigenous territories, historical Europe. There are lots of places where you don't have births by mother's age. You might have small area data that's masked for privacy reasons. In the US, for example, small counties, and I'm going to pick a county in Georgia, that's the smallest one, Taliaferro. You can't get births by mother's age because that would be too revealing. There are not so many potential mothers of a given age, and so it's masked for privacy reasons. And then last, a lot of social science questions involve births not only by mother's age, but also by other social categories. Kim, may I pause for a second? I have a technical question. Is there any way for me to have the admit from the waiting room messages turned off? They're obscuring my screen when people show up.
Oh, sorry. I will try to investigate.
I mean, I can live with it, but it's, I can't read what's on my slide.
We'll try to deal with them as quickly as possible. So
okay, fine. I shouldn't have even mentioned it. So in short, we often don't have the data we need to estimate TFR, but we might have the total age-sex structure. We might not even have any birth records, but we might know how many young children there are and so on. So we could start from an age pyramid I picked this one because I'm in it. I was born in 1959. I don't know if you can see my cursor, but I'm somewhere over here, male, 5 to 9 at this point. There's clearly evidence in this age pyramid of high fertility, simply because there are a lot of children per woman. You know, the newly born, the recently born cohorts are the big ones. In some way, it's obvious that this has to be a high fertility population. There's even a hint that fertility might have been falling a little bit if you look at the sizes of the youngest 2 age groups. So there's information in here that promised how to extract it in a sensible way. In this particular case, we have 18.4 million survivors of 64 to 68 births, and 47.9 million survivors among the potential mothers. This is assuming a closed population, or assuming that children and mothers always stay together when the child is under 5. In other words, if people had emigrated, we would assume that mother and child immigrated. If people immigrated, we assume that mother and child immigrated. So we're thinking about the fertility of the people who end up in this age pyramid at the end of a 5-year period. And it's important to think about the fact that these are survivors, because there could be maternal mortality, and in particular, there could be child mortality. That's been one of the big worries about using child-woman ratios to estimate fertility. Okay, so we have to think about how to extract the total fertility rate from that kind of a distribution. I'm going to do this in 2 steps. One is think about the mathematical relationships that are involved in the relationship, in the connections. And then second, think about a statistical model for the unknowns. Okay, so the second part is there's going to be dependencies on parameters that we don't know, but we might be able to produce reasonable prior distributions for those parameters. And as a result, we could possibly get a range of plausible values for TFR from the age pyramid. That's the idea, is we're going to set up a Bayesian model. We're going to say we know the data is the age pyramid. The unknowns are the demographic parameters. Just to preview, mortality rates, shape of mortality pattern, maternal mortality, age distribution of fertility, and TFR. Okay, if we, just to preview some more, with the 1964 to 68 period, which is what would be captured in the young children in 1968 for the US, we get a fertility rate that's in the high 2s as the most plausible, something like 2.95. That turns out to be a little bit higher than what was observed, but it was in fact fertility in the high 2s. Depending on how you average the years and whether you think these are July populations or January populations, you get slightly different numbers, but this is definitely the right range. And this is a pretty narrow range of values because we have a lot of people. Later on, we'll have only a few people and a very wide range of values. Okay, so let's think about the underlying mathematics of this. The key is to think of a projection step in a cohort component model to think about the Leslie matrix that we use in projections. And let's think about one particular age group just as an example. Suppose we're talking about women who began this 5-year period of interest in the 20 to 24, 20 to 25 age group, and are going to end it in the 25 to 30 age group. You might notice there's let's see if I can highlight this. No, I can't. There's a scaling factor K here. K is just something about the size of the birth cohort we're talking about. If we project forward to the end of the 5-year period, we expect proportionally fewer women to be there. And they're going to have some births during this period that's some sort of weighted average of the fertility in the younger and the older age groups. This is all very familiar. This formula here tells the total births. A familiar way of thinking about this is per blue woman, per initial person, how many births do we expect to have? That's the the entry in the projection matrix cell. And I don't know about anyone else, but when I teach this, this is always the hardest formula to sort of derive. But it's actually pretty simple. We're just dividing through by the number of women. The scaling factor cancels out. We get a weighted average of about 2.5 years at the lower fertility rate, or the lower age group fertility rate, and about 2.5 at the higher, but with a little bit of mortality weight. Here our problem is different. We know how many people are at the end of the period, right? So we don't want to divide by the blue group, we want to divide by the red group. That turns out to be a very similar looking formula, except that the mortality weighting goes on the first age group, and it's a little bit bigger than 1. Okay, but this is a familiar type of formula. It's just sort of expressed in terms of the ending population instead of the beginning. All right, just repeating that formula again for the sake of keeping it in our heads. Now we have to think about the fact that not all births survive. There's a simple correction factor for that. If we know the big L's in the life table, it's approximately the 5L0 over 5 is the fraction that we expect to survive. And so the final formula here, children per woman 25 to 29 at the end of the period, is the survival probability times this weighted average of the lower and younger fertility rates, or say the younger and older fertility rates. Okay, hopefully that's semi-familiar. If not, the big idea is that if we know fertility rates, mortality rates, and well, this is also mortality, the survival of children, we could estimate how many children we would expect to see in an age pyramid from the women in this age group. And I'll call that K25, meaning this is the expected number of kids per woman 25 to 29 at the end of the period, the ones we observe in the age pyramid. Okay, now we have to think about the age pattern of fertility. This is a little bit mathy, but won't be too bad. The total fertility rate is just 5 times the sum of the fertility rates in our, I'm going to use 7 age groups. It's convenient to define the fraction of lifetime fertility that happens in each of the 5-year age groups. I'm going to call these phi. They add up to 1 over the age groups. And then importantly for the next formula, that you can express the fertility rate in an age group as the total fertility rate times the fraction of it that happens in the 5-year age group divided by the 5 years. So this is births per woman year in age group A, expressed in terms of the TFR and the fraction of lifetime fertility that happens in that age group. All right, so we go back to our K formula. This is how many kids we expected per woman. We can re-express this in terms of those phis. Now we've got TFR in the formula. So we've replaced these F's with phi, TFR, and 5. That works out to something that is fairly simple looking. And let me explain why I think it's simple. This is survival of children. What proportion of births survive? This is lifetime fertility, the object of our interest. And this is approximately an arithmetic average of the proportion of fertility that happens in the 20 to 25 age group and the proportion of fertility that happens in the 25 to 29 age group, slightly mortality weighted. I'm going to call that last term P. Okay? And that's the fraction of lifetime fertility that was experienced in the last 5 years by the women who are 25 to 29 at the end of the period. And by the way, this will be approximately 1/7 if you have 7 age groups. On average, 1/7 of lifetime fertility happens over a 5-year period if women are fertile for 35 years. Okay, sorry, we're almost done with the math. Well, not quite, actually. Sorry, we're almost done with the Leslie matrix math. So just as a summary, the expected number of young children in the age pyramid per woman in some other rung of the age pyramid depends on two global factors. Depends on the lifetime fertility level and the percent who survive, the percent of children who survive. And then it depends on two age-specific factors, the fraction of lifetime fertility that happens to these women in the previous 5 years, and then whether they survived, whether the women survived. So we need the life table big L's, which show up in these formulas, and we need those fertility timing fractions, which is a simplex formula, but it's a set of non-negative numbers that have to add up to 1. This is where the statistical modeling ends up. We need some parametric way of describing these parts of the formula. I'll try to do this part fairly quickly. For mortality, it's convenient to use the Wilmoth et al. Two-parameter model, where Q5, the under 5 mortality rate, is one of the parameters, and a second parameter is a sort of shape parameter called K, which is much, much less important. In fact, they even have a one-parameter version of this, I believe. Okay. The constants A, B, C, V in this formula are predetermined. You just look them up in the Wilmoth article. So if you know Q5 and K, then you have a complete abridged life table. Take them, turn them into mortality rates, turn the mortality rates into the big L's that you need in the formula. Okay, so this is 2 parameters for mortality. The K in their formula is almost always between -2 and +2, so a standard normal is a perfectly fine prior for that. For Q5, you need some external information. You need to know, you need some guess, I've called it Q5 hat, of what under 5 mortality is. And my way of dealing with this is to say, all right, I'm going to say there's a 90% chance that the true Q5 falls between half and twice the estimate. In other words, I'm not putting a lot of credence in the Q5 estimate, but I'm using it to center the distribution in a sense, but with a pretty wide range. So here, suppose the estimate is 25 per thousand. We've got a wide range of possible values, anywhere between, say, 15 and 45 per thousand, something like that. Right. So this is a very loose prior. It's not tightly anchored to the estimated Q5, but it does need an estimate. Just some example draws from that prior. These are on the left. We have the big L's, life table person years in the 5-year age groups, and here we have child survival, which is very important. If Q5 hat is 0.025, we get a wide range of possible child survival patterns, like we just saw in the prior. Okay, let me pause and ask Jakob if there have been any questions so far.
Everything crystal clear by the sound of it. And
yeah, okay, yes, I'm used to that kind of clarity. I hope that's true. Okay, the next thing we have to parameterize, the next unknown, is the fertility timing. Remember that these are the fractions in each of each of these 7 5-year age groups. I propose using a model that's a lot like a multinomial logit model, where we talk about the log odds, and in this case relative to the fraction in the 15 to 20 group. So for each group we say what are the log of the relative fractions in each group. That gives us 6 parameters, which I've called gamma, that describe these 7 fractions, right? The constraint that they add up to 1 is why we only have 6 parameters. Here, what we did is we looked through the human fertility database, which is a wonderful resource for developing prior distributions, and essentially came up with a 2-parameter story about the timing of fertility. Now, remember, by the way, these are log odds. So if you look down this, is my cursor visible?
Yes, it is.
Okay, so if you look down this first column, it says the sort of baseline is that the log odds of fertility go up through the first 3 age groups, then go down and go way down in the highest age group. So this is a kind of standard age pattern. Here we have delay, right? If you multiply this column by some positive number, it makes the relative or the log odds higher in the older age groups. Okay? And then this one is a little bit about the variance. This says, is it more concentrated in those 3rd and 4th age groups or not? Okay, so there's sort of a level, which is a constant, then a shape, and then a mean, and then a variance parameter, basically. And one can scale these so that they have 0 means and unit variances across the HFD data. And then the prior we're going to use is a independent standard normals for these 2 betas. Okay, so this gives us a way of developing the shape of the fertility curve. Right? If you give me these 2 betas, I can convert them into gammas. Then, if that's log odds, then turn that into probabilities, and we get draws like this. These are all sort of plausible patterns of fertility by age. We don't know what the right pattern is. We don't know whether the young women in the age pyramid experienced a relatively high fraction of their fertility in the last 5 years or not. But what we're going to do is sort of average over all these possibilities with the prior. Okay, so here's the overall picture of how to estimate. There are 5 demographic unknowns, one of which is the overall fertility level. That's the object of interest. 2 of which determine the shape of the fertility age pattern, 2 of which determine the shape of the mortality schedule. The level and age pattern determine our rates. The rates together with the mortality determines how many expected children per woman in each age group. Then here we have data. We know the age pyramid, and we know the number of children in the age pyramid. We're going to assume that that number of children is a Poisson draw from with a parameter that's the expected number of children at the current levels of the parameters. And the idea is we know W and C. That's what's in an age pyramid. That's the bars we started with. What we don't know are these 5 things. We're going to just find the more and less plausible combinations of these and then look at the marginal distribution of the total fertility rate. Which TFRs are the plausible ones given the number of children and the number of women in each age group. Okay, so that's the applications. I'll go through 3 quick applications of this. We can do TFR for small areas, like counties in Georgia where we don't have complete data on births by mother's age. We can do historical data where we don't have any vital registration, but we might have population counts by age. We can do TFR estimates by social variables. And we can do TFR for very, very small populations, which is the application I'm going to talk about most. But let me run through these first 3, just sort of proof of concept for these first 3 quickly. It's sort of fun. Okay, Georgia in 2010. I have an age pyramid for 159 counties. That is, I have 159 age pyramids. They range in size from a couple hundred women to a couple 100,000. We have Q5 estimates from public health systems. And when we estimate total fertility based on the age pyramids of the counties, we get a pattern of variability from anywhere of a TFR of 1.4 to 2.7 for Georgia counties. what we learned is fairly plausible, which is university towns have low total fertility. And that's because they have a lot of women 20 to 24, 25 to 29 who are delaying childbearing. So there aren't a lot of children per woman in those counties, and those tend to be the places with the very lowest fertility. I'll give you one sort of side note. We did this for very small areas, and it was possible to identify the university census tracts, which are very much smaller areas, because they had TFRs of 0. There were no children in their age pyramids, because everybody in that small area was living in a university residence. So by definition, there weren't any children. The highest fertility in Georgia is a place where there's an Army base, U.S. Army base. This is a place where there are a lot of women who are not in the labor force. They're military spouses. They tend to have very high fertility. And then another low spot we found, turns out there's one of the biggest women's prisons in Georgia is in this state. It's a small county, so a fairly high fraction of the women in that county's age pyramid are in jail. They don't have kids at high rates either. And then metropolitan areas tend to have lower rates. So this is the result of doing 159 analyses of age pyramids and analyzing the distribution that comes out of them, and then thinking about what the plausible TFRs are. So it's an application, a direct application of the model I just showed. Here's historical data for France, Italy, Netherlands, and Sweden. This is a tiny bit complicated to explain. All of these countries are in the Human Fertility Database, and to the right of the dashed lines, we actually have total fertility rates reported from the HFD, but all of them are also in the HMD, the Human Mortality Database, and in the Mortality Database, we have age pyramids. So what we did is we estimated the fertility rate from the age pyramids for all of the available data to the right. So these black lines are our Bayesian medians. The gray bands are the uncertainty, or the 90%, or maybe it's 80% uncertainty band. In all cases, we match recent fertility quite well, although there might be a slight lag. It's hard to tell with these symbols. But we can go back, hundreds of years in some cases to estimate fertility way before there was any birth registration in these places. And this is a potentially very interesting use of this method. And it seems to be finding things properly because we also have the Human Fertility Collection, which is a sort of not gold standard, but pretty good set of information, a set of estimates. And we seem to be tracking in France very well, in Sweden fairly well also. So it looks like we're getting it right with this, with the plausible levels of TFR given the age pyramid. And then last of my first 3 examples, we can look at information that's not on the birth certificate and learn about social processes. This is U.S. total fertility by race and household income, whites and non-whites. This is annual income in thousands on the horizontal. And we see this interesting U-shaped pattern. This is estimated from a data set that has no birth information in it at all. There's no question on births in the last year. There's no question on children ever born. It's just the number of women and children in households defined by income and race. And you see this interesting U-shaped pattern where it's the poorest and the richest families that have the highest fertility, and it's consistent across race. And there's also a little bit of a non-white bump. So in short, I'm going to go back quickly. This is something you can't do with vital statistics because of privacy. This is something you can't do with vital statistics because they don't exist. This is something you can't do with vital statistics because we don't ask for income on the birth certificate. Okay, so all of these are potential applications that are opened up by this sort of careful thinking about how the age pyramid is related to fertility. Okay, so to sum up this first part, and I better hurry, you can estimate TFR from the age pyramid. This is an indirect estimate if you think about it. That's not super novel. Everybody knows that if there are a lot of kids per woman, there's probably a high fertility rate. There's a wonderful article by William Brass from about 50 years ago that describes something similar to the Lexis, not Lexis, the Leslie math that we did. But what's new here is adding the statistical element, adding the uncertain part, the parameters in the formal demographic relationships can be made into distributions by exploiting what we know from these big public data sets. So we can derive priors for the unknowns from the big collections of data that we now have. And that means we end up with a model that tells us not only about the most likely value, but also about the uncertainty. And I'll highlight that next. All right, now I want to switch to talking about applying this to indigenous fertility in Brazil. This is an ill-fated paper, let's say, that has not been finished yet for various reasons, partly having to do with the fact that the first author, Martha, is a very involved activist in indigenous affairs and is always distracted by very serious crises, let's say. But the three of us have been working on this paper to try to estimate for the first time ever indigenous fertility for all indigenous populations in Brazil. There have been, anthropologists doing one-off estimates, but here we're trying to do something comprehensive. And the reason we can do this is because Marta, co-author, was a government minister, and she lobbied the Brazilian Census Bureau to do better at counting the indigenous people in Brazil and getting those age pyramids that we would need. A little bit of background. Portuguese arrived in Brazil in 1500. At that time, there were about 1,000 indigenous ethnic groups, estimated population of about 3 million. They have, been not literally decimated, but very, very, very sharp population decline as a result of disease, land occupation, and so on. There are now about 300 ethnic groups, about 1 million indigenous people, and they're divided into very, very small ethnic subpopulations, some of which only have dozens of people. But the big concern is whether the fertility of these groups is above replacement. Are these populations recovering in the 21st century? That's the biggest question here. I want to describe briefly a little bit about the categorization of indigenous people in Brazil, because we're going to exploit it in our Bayesian model. There are two major language groups that are coherent in Brazil. There's Macro-G language and Tupi languages. There are a lot of indigenous groups don't speak their native language anymore, speak Portuguese. And then there are lots and lots and lots of sort of miscellaneous language groups. Each of these are called trunks, and then there are lots of Macro-G languages. These are language families, and then languages within the language families. But they basically fall into these four groups, or at least the way we've done it. Portuguese is not an official ethnic indigenous group, but we're going to use it we're going to use language as our sort of cultural marker. These linguistic differences are important proxies for cultural differences. And the one I really want to highlight is all of these groups have marriage patterns where people marry outside their village. So all marriages are between villages. In the Tupi cultures, married couples live in the wife's village. That's called uxora locality. Uxor is the ugly Latin word for wife. And in the Macro-G linguistic groups, the couple lives in the husband's village. And that may make a big difference for fertility, in particular because in the Uxore local, which is the Tupi system here, women have more support, sisters, relatives around. It's more likely that they would have early fertility rather than wait because they're living in a strange new place with strange new people. I'll just leave it at that for the moment. So the Tupi are the ones that might have the higher fertility because of the Uxore locality. So you can tell one of my co-authors is an anthropologist. That's Marta. All right, indigenous people live all over Brazil. There are the Portuguese speaking tend to be in the Northeast. There's one very big group in the Northeast. The balls are proportional to the number of women. The Macro-G people live all over, Tupi people live all over, and then these other groups tend to be these very remote Amazonian peoples. The biggest of which is the Yanomami, which you probably have heard about. That's the sort of most famous group. I want to highlight for the moment that down here in the south, there's a Tupi cluster and then some others. So we might expect, if the cultural model is right, that the Tupis would have higher fertility and the others in that area would have lower fertility. That's sort of the anthropological theory. Okay, I'm going to try to finish in 10 minutes. In the 2010 census, because of my co-author's advocacy, there are improved questions on Indigenous identity, and very importantly, there's improved census geography. So now the census sectors, they're called in Brazil, are aligned with the Indigenous territory boundaries in a way that allows us to get only Indigenous territory populations. And we're going to focus on those. These Indigenous territories are now identifiable. We know which ethnicity goes in which territory. And so the idea is we can use the age pyramids in those census geographies to estimate the fertility of the indigenous group that lives there. I'll sort of do this quickly. Brazil has both a long form and a short form. The long form is a sample that's given to, I don't remember, 10% of all respondents. It does have direct fertility questions, but for these very small groups, we just don't have enough data. These groups are small enough, we really need to use the short form data. And in that, we have age, sex, and literacy, turns out. Okay, so we're going to use this age, sex, literacy, the age pyramid. We're going to use the model that we developed with the uncertain parameters and the priors, and we're going to estimate exactly as before, but we've added what I call cultural priors for the TFR, a kind of structure where we think that tribes that speak languages that are more similar are more likely to have similar TFRs a priori. So instead of spatial shrinkage, we're going to have cultural shrinkage, so to speak. Or instead of borrowing information from nearby spatial places, we're going to borrow information from culturally nearby groups. And then we're also going to use literacy as a covariate in the model in a standard way. Okay, and then we'll look at the marginal posteriors. Okay, here's a quick example. We've got to identify which sectors belong to the indigenous territory. We've got to identify what ethnicities and languages are spoken there. This is one example. This is a place called Aripuanã. We know what language is spoken there, what language family, and this is a Tupi area. Okay, and just for scale, this is a little bit lame, but there is the UK in comparison to this area. If I figured it out right, this is about 1/3 the size of Wales or half the size of Northern Ireland. keep that in mind when I show you how many people live there. Right, so this is an area, a big area. There are 18 women, 15 to 19, 10 women, 20 to 24, and so on, living in this area. And this is like the lowest density population you can imagine, right? 64 women total and 55 children enumerated in the 0 to 4 range. And then among the young women, about 2/3 are literate. So very, very, very small, very, very, very low density population. If we do our model without the culture in it, this is what we get. In other words, if we did exactly what we did before for the US age pyramid, we see the most plausible TFRs are in the high 5s to 7 range, but it's possible that TFR is 7.5. It's possible that it's 5.2. There's a lot of uncertainty here because it's such a small group, and we really don't learn much that we can be sure about. But we know this is well above replacement. Right? That's virtually certain. Plausible demographic parameters lead you to TFRs that are well above replacement, and in fact, probably almost certainly above 5. Right? Probably above 6, and so on. Just for kicks, if you take 7 times the total number of children by women, you get 6.02. That's right here. This is almost always a really good estimate. So the simplest thing you can do is just take the children per woman, multiply by 7 age groups, and you get something close to the TFR usually. This is due to that 1/7 that I talked about before. Okay, for the cultural model, what we're going to do is basically say TFR has this structure, that there are trunk effects and then family effects and then language effects and place effects. Basically, that we're going to model this sort of correlation structure culturally, that the language they speak is related, that connects their TFRs so that it's more plausible that a set of TFRs is right if it gets the culturally similar groups with similar TFRs. Okay. When we add culture to the model, these are the TFRs we would estimate for the 450 something places if we didn't use culture. And by the way, notice we've got some Hutterites here. Some groups have estimated TFRs above 10. The main function of the cultural model is to pull those high ones down, that those are probably implausibly high when we look at the other people in their cultural groups, and as a result, the shrinkage is, tends to lower the very high ones, but they're still very high. There's still some estimates near 10 or 9. Okay, so these are very high fertility populations. The overall picture is, yes, indigenous fertility is way above replacement in almost every place, given the child-woman ratios and the patterns in their age pyramids. Okay, I'll abbreviate this. These are our 4 major cultural groups. The Tupi groups, the blues, tend to be higher than average TFRs. The Macroje tend to be lower than average. The others tend to be higher average, and the Portuguese-speaking tend to be lower than average. These are the sort of these fuzzy balls are the trunk effects, and then on top of that we have these family effects. The main point is that it does seem to work. The Tupis, which are the Uxora locals, are higher. The Macroje, which are the Vera locals, are lower on average. Okay, here's every territory. You can see that there's a lot of uncertainty. Right, every point here in the center, the dark points are the posterior median. The bands are the 90 or 80% uncertainty intervals. Some of these places are extremely small and we have very, very high uncertainty, but nonetheless, we can probably rank these loosely. And I'll do this quickly. The Portuguese-speaking ones tend to be lower. Macroje ones tend to be lower. The 2p ones are clustered a little bit higher. The other, the miscellaneous are higher still, and the super high ones are all these miscellaneous Western Amazonian, very, very remote tribes. Okay, and if we look at by territory, the color scale here is the bluer and the cooler colors are low fertility. The warmer colors are high fertility. We see some super high fertility out here in these very remote Amazonian places. The Yanomami, that big group, 6 to 8, so that's super high fertility. The Portuguese-speaking groups, which are tend to be the most assimilated, they live in more urban-like areas, for example, have low fertility. And then in that cluster I highlighted, the 2p group in the middle is the one with the high fertility, and the other groups and the Macroges have the lower fertility. So to some extent, that cultural theory again is showing up here. Okay, so because we have this new data, we can do this. And in fact, I should say this was this indigenous analysis was the inspiration for all of this. The reason I started thinking about the problem of estimating TFR from the age pyramid was because that was the data we had for the indigenous people. And that is thanks to my co-author, Marta. She actually, not only knows how to analyze it, she made sure that the government collected the data. Second conclusion, indigenous fertility is definitely high relative to the rest of Brazil, which is slightly below replacement for non-indigenous populations. The indigenous fertility is well above replacement, but there's a lot of variation. And then this cultural story seems to match anthropological theories. It does look like the Uxora local cultures tend to have higher fertility after controlling for literacy. Okay, thank you. That's the end of the presentation. I want to introduce my co-authors, Marta Azevedo, Matt Hauer, my colleague at FSU, and Joe Potter, who is at Texas. Everybody contributed to all of that, everything I've just said. With that, let me stop sharing and see if there are questions.
Thank you.